Welcome to your video lecture on plate tectonics. This is Chapter 7, Part 3. Alright, not a lot of information in this video, so let's go ahead and get right to it. Your very first question is, what are the three types of rocks? Describe how each is formed using appropriate vocabulary terms. Alright, hopefully this is familiar to you from middle school. You've got three kinds of rock. You've got igneous rock, you've got sedimentary rock, and you've got metamorphic rock. Igneous rock is that comes from cooled lava. It's basically directly from the source. Examples of this are things like basalt. That's B-A-S-A-L-T. Definitely know that for the national exam. Second kind of rock is sedimentary rock. This is formed from layers of weathered rock bits fused together through compression and crystallization. An example of that is limestone. We've got a lot of that here in southwest Florida. And then the last kind is metamorphic. This is either igneous or sedimentary rock, sometimes even another form of metamorphic rock, that has been changed in form through great heat or pressure. Some examples of that are marble, which comes from limestone, or slate, which comes from a rock called shale. So be aware of where they all come from. Again, igneous, straight from the source, lava. Sedimentary is where it's kind of been ground up through the action of rocks moving against each other and wind and water rushing against it, and then it's pressed together like a layer cake. It's in sedimentary rock that we oftentimes see things like fossil records. And then metamorphic is another kind of rock that's been put under intense heat and pressure and has changed in form into something else. Alright, question 2. Differentiate between magma and lava. All you got to remember is same stuff, different location. So, it's that same liquid, gooey rock. If it is below the surface of the earth, we call it magma. If it is on the surface of the earth, we call it lava. Next question. Identify the three parts of the lithosphere and their locations. On the left-hand side is the different parts I expect for you to know here on this slide. On the right-hand side of the slide, sorry about that, are some things that may be referred to on the national exam, so I'm kind of putting this up here. So if and when you review these videos right before the exam, you can at least kind of see this, and maybe if a question like this pops up on the exam, you'll be like, oh yeah, that thing. Alright, so let's go ahead and talk about the left. Three parts of the lithosphere you need to know about. So I'll start from the inside, the core. The core is the molten center of the earth. It is largely made out of iron, and then it's covered by the molten mantle. This is, again, molten rock, largely made out of silicates. Silica is the main component of sand, and this is always heating and cooling. The part of the mantle that's up against the core gets hot and moves up. Now it cools as it gets closer to the surface of the earth, which is called the crust. And when it does that, it cools and it falls back down towards the core. So that mantle is always moving. Think about it like simmering gravy, where you get bloop, bloop, a bubble every here and there. The crust lies in pieces above the mantle. And we're going to take a look at what those pieces look like momentarily. Your book suggests that you think about an orange that's been peeled, and the peel is then torn into bits, and then the bits are put back onto the orange, and how you can kind of vaguely slide those bits around the orange while kind of keeping its form. I suggest you think of, and as gross as this sounds, you'll absolutely remember it, graham crackers on gravy. So imagine you've got a graham cracker, you crack it up into 5 or 6 pieces, and you lay it on top of that slowly simmering gravy, and you're going to notice that the pieces do kind of move around and bump up against each other because of the action of the gravy. And we're going to talk about what the name is to that hot mantle rising, cold mantle falling momentarily. Okay, how did the Earth's terrestrial surface look millions of years ago? It was one supercontinent called Pangea, and that's the thing there on the right-hand side. The link, you are welcome to stop this and go ahead and watch that on your own. I'll also make sure I play that in class. I do not expect for you to know that Pangea broke into Gondwanaland and Laurasia. One thing you do want to notice there on the pictures on the left is that India is its own piece, and that is going to become important here in about 5 or 10 minutes. But just know that all of these guys were together into a supercontinent called Pangea, and we will talk about the dude who came up with this at the end of this presentation, because he is not in your book. All right, here is answering the question, how do they turn into today's continents? That would be continental drift through the action of convection. So all of those graham cracker bits on that gravy eventually move to other places because of convection. When hot liquid rises and cold liquid falls, creating that motion, that is called convection. So it's not magic or magical fairies. In this case, you actually need to know that it's called convection. And that's what causes the bits of the Earth's crust to move around. And I may as well tell you this now, those bits of the Earth's crust, those are called tectonic plates. That's why this is called plate tectonics. All right, be able to describe this process, the mechanism for how this took place. There you go. All right, sorry about that sound. My husband's computer apparently decided to talk to me. So, moving on. Here is that idea of the orange that that your book was referring to. That's kind of what it looks like. Okay, location of the plates. Get your textbook out and look at the map on page 200. I will wait. No, I'm not kidding. Go get your book and open it to page 200. Okay, you're back. You need to know the major plates, and here's what I mean. You need to know that North America sits on the North American plate, and that does include Florida. Africa is on the African plate. Eurasia, which would be Europe and Asia, is on the Eurasian plate. Australia is on the Australian plate. Here are the things that you really need to note. Please note that India is on the Australian plate and not on the Eurasian plate. Why is this important? Because we're going to talk about what's happening on the border between India and Eurasia. Be familiar with where the Pacific plate is, also the Cocos plate and the Nazca plate. Those are going to come into play here momentarily. Also be aware that tectonic activity, and we're going to talk about that in a minute, like volcanoes and earthquakes, only occur along the plate edges, which is why we don't get earthquakes here in the state of Florida. We're not on a plate edge. However, poor California, as you can see where it is right there on the edge of the Pacific plate, that's why they get a lot of earthquakes there, because of the action between those two plates. All right, so again, know where those are. And let me go ahead and take care of a shout-out request. Miss Dominguez said, hey, can you put in a science joke? Here you go. I told a chemistry joke. There is no reaction. Okay, here's one more. Seriously, dude, I think you're overreacting. I can feel your disappointed glares coming from here. I will do a better job next time. That one was for you, Miss Dominguez. All right, moving on. Let's talk about plate tectonics in action. You can either look at this or you can look at page 201 in your book for pictures. There are 3 types of plate movements you need to know: divergent, convergent, and transform. Don't worry, you're going to learn to cheer about all of these. This is all of those boundaries put together. So let's talk about each one. Describe what happens along divergent plates. Shockingly, they move away from each other. And what tectonic activity or activities are associated with this type of boundary? This is associated with seafloor spread. So wherever this usually happens along the ocean floor, and when the plates move away from each other, magma comes from under the ground, moves up to the surface of the plate, and that side of the plate gets bigger, so the seafloor spreads. This is why North America and Europe every single year get a couple feet farther away from each other. Now, this is not in your book. I'm not going to have this on the quiz, but this is just to kind of show you the impact that plate tectonics have on our ecosystem. There is a divergent boundary in a place called Afar, Africa, and you can see where it is right here. You've got Yemen You've got the Red Sea right there, and probably one of my favorite places to stay in Africa, Djibouti, is a place called the Afar Triangle. It's where three plates touch, and they're all moving away from each other. So here's what's happening. The Nubia plate, the Arabia plate, and the Somalia plate are all moving away from each other. There is a rift that is occurring there. And if you look, those people are scaled appropriately there on the left-hand side of that picture. So you're like, great, what's happening here? Toxic fumes and other chemicals are coming out of that rift, which is basically making that area uninhabitable. And eventually, that little bit that is there on the corner of Africa, which would be this guy, is eventually going to become an island thousands and thousands of years from now, once all of these plates are done moving away from each other. So you can imagine the impact that this is having on this ecosystem. Yeah, it's not fun. So most of the time it's seafloor spread, but just do be aware it does on occasion impact land forms. All right, the second type of boundary we're going to talk about is transform plates, what tectonic activity or activities is or are associated with this type of boundary. Plates rub up against each other. However, it is not like they're smoothly moving next to each other, like some sort of, like if you take your hands and put them together and then you rub them to make them warm for those 2 days of winter that we have here in Florida, that's not what this is like. What it's like instead is, imagine you have 2 blocks of wood with sandpaper on it, and you push them close to each other, you push as hard as you can, and then you start trying to rub them against each other. You're going to find that the tension builds up, and then all of a sudden the blocks fly apart. That is how these boundaries work. So it is a buildup of pressure that suddenly releases, usually as an earthquake, which is when that release of pressure happens on land, or as a tsunami. A tsunami is water activity that's associated with a seafloor earthquake. An example of this would be the San Andreas Fault. If you look at these 2 black arrows here in the graphic on the left-hand side, one bit is moving kind of in the northwest direction, and the other one is moving in the southeast direction. Eventually, if this continues, excuse me, San Diego keeps getting closer and closer to to San Francisco. So those 2 cities are slowly but surely, and Palm Springs and San Francisco will eventually be next to each other. And then here on the right-hand side, you can see what the San Andreas Fault looks like from space. Earthquakes are not something we experience here, so what you need to be aware of is this. There is one shock, which basically makes things like concrete ripple, like putting a flat sheet on your bed. If you make your bed and put a sheet on it, you usually will snap the sheet so it kind of does this wave-like roll so it goes across your bed. That's what the ground does. But it's not over then. After the massive destruction, you have what are called aftershocks. And there was an earthquake in Japan a couple years ago, which damaged a nuclear power plant. We'll talk about that another day. That had aftershocks multiple times a day for almost a month. So imagine what this is like. You have an earthquake that has completely destroyed everything, and now you're trying to rescue people and clean up, and as you're doing this, every hour, sometimes every minute, you have a little tremor again that's causing everything to shift and just freaking you out again. It is, you can't even imagine. Tsunamis create a wave, except it's not a wave as much as it is a wall of water. That force gets translated to the surface of the ocean as a literal wall of water that goes in. Tsunamis can go upwards of a mile or so into the inland, and then it recedes again. It goes back out. So it basically takes everything it's destroyed and pulls it back out again. So the ocean becomes polluted with all of that stuff, and then the land that the wave dragged itself across basically is wiped clean. It's a devastation you can't imagine. So we're going to go ahead and watch this stuff in class. Here's an earthquake that occurred in Haiti 4 or 5 years ago that the country is still recovering from, and you can see here on the left-hand side a before and after picture of the Capitol building. And then here on the right-hand side, this really looks like somebody unfortunately took the entire country and then kind of shook it up in a shoebox and then let everything fall out again. It's pretty devastating. So we'll talk about the impacts of this in class as well. Landslides can also occur from earthquakes, and you can see here the entire side of this mountain just gave way. And these little things down here are houses, and you can see some people's houses just basically got covered up by the mountain. And here on the right hand side, you can see how tsunamis work. You do not need to know this in its intimate detail, like you have to know the nitrogen cycle, but just be aware of how the force translates to the surface. And we are going to watch a video on Fukushima, Japan, and the tsunami that they had to deal with. And you can again see the destruction is just almost unfathomable. Alright, and then the last kind of boundary is called convergent. And this is where the two parts of the plates come, towards each other. And there are two things that can happen. You can have subduction, which is the picture there on the right-hand side, where one plate is basically forced under the other one. Think about what's happening, and this should make sense to you. If there are parts of a plate that are getting bigger because of divergence, then the other part of the plate has to get smaller because the Earth is clearly not getting bigger. So, part of the plate goes, one kind of goes on top of the other one, and the plate that goes below is melted back into magma. It kind of recycles. Or the two plates can push up against each other and create a mountain range. We have mountain ranges such as the Himalayas, I'm going to talk about in a second, which are still growing by inches and feet every single year. Activities that are associated with these types of plates. Subduction is associated with volcanoes, and again, the kind of conversion that make mountains, mountain building is associated with those. Alright, so volcanoes. Brief thing about this. Volcanoes are either active or not active. When they are active, you can either have some that kind of run all the time, like this one here on the right hand side, or you can have some that suddenly blow. Now, let me back up a second. All of this tectonic activity, things like earthquakes and volcanoes, our ability to predict when these things are going to happen is in a matter of seconds, not even a minute. So we have the most sophisticated equipment you can imagine, and we are unable to accurately predict when these things are going to happen until we just go, brace yourself. That's really all you get. That volcano there on the left-hand side is I'm going to completely destroy this name. It's like Patanabu. I'll look it up. We're going to talk about this later on. That is in the Philippines. And its explosion was so violent, and here you can see it's miles and miles away, that the cloud of ash that was pushed into our atmosphere went high enough that it stayed in the upper atmosphere for almost a year, and that ash was so thick that it reflected enough of the sun's rays to cause a global temperature drop on average of 1 degree. So if you averaged everybody's temperatures and compared them to years past, everybody's would be a degree lower. So again, absolutely an impact on our environment. Okay, here are the Himalayas. You can see a panoramic picture of them. Where are they located? They are located on the border between India and the rest of Eurasia. Why? Because remember, India is a part of the Australian plate, and it slammed into Eurasia millions of years ago. And it is the Himalaya mountain range. That mountain range continues to grow at a rate of 1 to 6 centimeters every single year. So if you climb the highest mountain in the Himalayas, you're like, yes, I totally got to the top of that one. If you wanted to maintain the title of having climbed the tallest mountain, you would have to go back every year, because that mountain is just going to keep getting taller and taller and taller. All right, here are the Himalayas from space. We're going to talk about why this is. If you look, one side is very, very green. That's the India side. One side is, this is a cold desert. That is Tibet, which is right on the outside of China. There is a reason for this. We're going to talk about it in the next section of this particular unit. Okay, I'll talk about this in class again, but oh so briefly, there's this dude whose name is Alfred Wegener, and he looked at a map of the world and he went, South America and Africa, if you cut those two continents out, you could actually kind of fit them together real nice. That doesn't seem like it's a coincidence. So he went around to all of the continents, and you can see he even went to Antarctica. Dude's all wrapped up in fur, and he dug up fossils. And when he plotted where they were on a map, he basically cut out all of the continents and fit them together, and by gum, where he found all of these fossils fit when he put them together into the supercontinent of Pangea. It took decades before people actually believed that this happened. Oh, by the way, if you're only watching right now on the way to school so that you can do well on the quiz, you can stop here. But all the stuff I'm talking about right now is going to be on your next unit test. All right, so Alfred Wegener, the dude who came up with the theory of continental drift. In other words, that where the continents are now is not where they always were. And then his proof was fossil records, and he's the one who posited or theorized that the supercontinent of Pangea, Pan meaning all, Gea meaning Earth, existed at one point in time. So what does that mean? Millions of years from now, our continents are not going to be where they are right now. When we start talking about things like biomes and climate and weather, we'll talk about the consequences of those in terms of where continents are located. All right, Ring of Fire. We're going to be doing an activity on this in class, so you should be pretty well versed as to what this is before the unit exam. But take a look at where the Ring of Fire is on this map. You're going to see it's largely the Pacific Plate, but also the edge of the Cocos Plate and the Nazca Plate. You're like, great, Morris, I could see what it is. What the heck are you talking about? 70% of the world's active volcanoes are found along the Ring of Fire. Thus, it's called the Ring of Fire. And then also most of the world's earthquake activity. So if you do not like earthquakes or volcanoes, stay away from the Ring of Fire. So be able to recognize that on a map, understand the implications of that, what's going on along those specific areas. So if volcanoes and earthquakes happen here, that should tell you that this is largely transform plate activity, and then also subduction zones. Last thing to talk about that's not in your book is something called a hotspot. If you take a look at where Hawaii is in the middle of the Pacific Plate. So you're like, how the heck do they have active volcanoes? I'll tell you why. Because there is a hole in the plate right there. So this plate is constantly moving, and it is moving over a hole, or the plate is moving over a hotspot, basically where magma is welling up through a hole. So that means that is how the islands of Hawaii formed. They're over this kind of plume that's coming up through the bottom of this plate. What this also means is that the Hawaiian Islands are continually growing. If you think about this plate moving very slowly and this magma coming up to the surface of the ocean, side note, is everybody here aware of the fact that islands are not attached by chains to the bottom of the ocean floor? They're like these large mountains that poke out the top of, or I guess, out of the ocean. So they grow from the bottom. Okay, so anyway, as the plate slowly moves over this plume, you've got the mountains that are poking out. You're like, great, Morris, who cares? Here's the answer. You should care because the islands that have moved away from this plume, the volcanoes no longer work because they're dormant, because they're not connected to this hotspot anymore. So that means the part of Hawaii that's still over this hotspot is where you have the most active volcanoes. What this also means, and if you look at this picture, you're going to see something that's called Loihi. This is an island that has not poked up yet. So that means in however long it takes, you're going to have a new Hawaiian island that's going to pop up, and through processes we're going to talk about later, be covered up in new life. We're going to talk about what we're going to do with secret questions a little bit later. I'm not going to go over that one right now because it's going to be kind of meaningless to you. But dude, we're done. Go to bed, or even better, don't be late to class. Bye, guys.